Good afternoon. I'm Regina from Lithuanian Energy Institute. Together with my colleagues, we prepared a short presentation about potential of oil shale ash and acid-based geopolymer production. Culture's oil shale is primarily used to extract shale oil, or it can be used as a fuel for heat and electricity production. However, mineral content of oil shale is more than 50%. Therefore, after combustion, it produces a large amount of ash. A significant part of ash belongs to bottom ash. It possesses no economic value and therefore landfilled. Meanwhile, finer fraction of this ash has potential application in civil engineering projects. The problem arises when, due to environmental, economic, or technological reasons, oil shale is blended with other fuels, such as biomass, that results in significant changes in chemical composition of residual ash, and it reduces its utilization possibility in cement industry. Ash derived from Lithuania power plant is rich in calcium-bearing phases. Therefore, geopolymerization in alkaline medium requires an additional source of silicate. Therefore, this study focuses on the evaluating of oil shale ash as a potential binding material in processing of acid-based geopolymers. Materials and methods. Materials used in this study were metakaolinite, oil shale ash, acid activator, and typical analysis methods like SEM, TGA, X-ray retrieval analysis, and also mechanical strength measurements. Based on our previous study, as received ash is rich in calcium-bearing phases, the content of which is nearly 45%. Particles are of various shapes and size, ranging from 4 to 35 micrometers. Mineral composition of ash indicates its limited application for acid-based geopolymers without additional pretreatment due to CO2 gas generation and temperature increase. Therefore, based on theoretical calculation, pretreatment step with 2 mild acidic solution was incorporated. We used 2 acid solution nearly 8 and 12% concentration. The ash treated with the mildest solution was denoted as ash 1, while with stronger solution as ash 2. X-ray analysis show that calcium is nearly fully consumed, and also we see peaks of brushite, which is almost stronger in ash 2. Electrical analysis revealed that acid concentration significantly affected mineral composition. A slightly higher acid concentration increased brushite content up to 3 times. On the contrary, content of amorphous phase was reduced up to 4 times. Compounds like stadinite, anhydrite, and calcite still remained. Here we see the after analysis of ash before and after treatment. We see that after ash treatment, there is no longer OH stretching vibration coming from Portlandite. We see characteristic symmetric and asymmetric stretching vibration of OH bonds from water, stretching vibration of PHOH or hydrogen phosphate ions, also most characteristic hydrogen phosphate ion band coming from brushite, also from water, asymmetrical CO stretching from calcite reduces, and the range from 1100 to 1000. Several compounds share the same bonds. We can find symmetric PO stretching from phosphate, asymmetric stretching of COC typical for quartz, also asymmetric stretching vibration of TOT very characteristic for cyanidine, and may also be sulfate ions typical from anhydrite. Asymmetric bending of phosphate ions are around 600. TGA analysis of treated and untreated ashes show that mass losses are around the same temperature, 200, 400 and 700. Brushite was obtained after acid treatment and its decomposition occurs around 190 degrees. The mass losses around 400 corresponds to Portlandite decomposition, and it is typical for raw ash. It's absent in treated ash. However, there are two small endothermic peaks indicating the composition of anhydride calcium phosphate to calcium pyrophosphate. The last peak, around 700, corresponds to the composition of calcite. In ash 1, it shifts to higher temperatures, suggesting some transformations during ash treatment step. The stretch curves in TGA imply that anhydrous dicalcium phosphate of anamorphous phase was formed during the acid pretreatment of ash 1. This is combined with a shift of calcium pyrophosphate crystallization to a higher temperature, particularly in ash 1. For mechanical strength measurements, geopolymers were prepared with varying metakaolinite replacement levels using both types of treated ashes. Samples were cured at two temperatures, 50 and 90 degrees. Microstructure analysis was performed on geopolymer samples heated up to 200 degrees. X-ray analysis of the reference geopolymer revealed that at lower temperatures anamorphous phase prevails. Few peaks corresponding metavaricite formation was detected only at 130. The formation of phosphocrystalline having the same chemical formula as berlinite started nearly 200 degrees. FTIR analysis show symmetric and asymmetric stretching vibration of OH bands and HOH banding vibration of water in geopolymers heated even at up to 200 degrees. Phosphocrystalline is characterized by a porous microstructure, which was also observed in our samples, thus implying the formation of PO aluminium OH instead of PO aluminium O units. The impact of treated ash on geopolymer phase composition was hardly visible in XRD curves. Metavaricite was not detected in modified geopolymer samples at 130. The main distinction is a small halo between 20-25 degree angle after treatment at 200 degrees. FTIR analysis did not show any significant differences among samples. Nevertheless, TGA analysis show a much broader but lower endothermic peak for samples with ash incorporation, suggesting alteration in geopolymerization reactions. These alterations are seen in compressive strength results. Data comparative to the reference phase are presented in the table. It can be seen that the curing at higher temperature and incorporation of lower percent of ash results in strengthening. High replacement levels reduce strength significantly by more than 50%. A change in failure mode from brittle to ductile was observed. The exception is the sample set with ash 1, which shows strength comparable to the reference at those very low replacement levels. An increase in strength after curing at higher temperatures suggests continued dissolution, possible dissolution of amorphous phase and calcium-bearing minerals, facilitating geopolymer structure formation. The loss in strength for samples with the highest dosage of ash was due to unhomogeneous, partially reacted structure. The presence of anhydride particles close to the amorphous gel was also observed, thus explaining the significant loss in strength. Based on the obtained results, we can conclude that ash requires pretreatment before its application in acid-base geopolymers. Partial pretreatment with a weak rather than stronger phosphoric acid solution results in formation of higher content of amorphous phase and lower content of brushite, making it more suitable for use as solid precursor. Curing at higher temperatures contribute to strength development of modified and unmodified geopolymer samples. Thank you for your attention.